so today the learning objective is to explain if a group is activating or deactivating, which means electron donating or electron withdrawing, and also to see if it's ortho, para, or meta-directing based on intermediate stability. We've gone over simple electrophilic aromatic substitutions like this one. So now it's important to investigate the outcome of the reaction if the benzene ring we're accustomed to seeing at the start of the reaction has a substituent. The first thing we'll go over is to see if a substituent group is activating or deactivating based on electron activity. We will observe how activating groups increase reaction rate relative to hydrogen atoms in the benzene ring by electron donation. This can occur by both an inductive effect or lone pair contribution to the ring. We will also see how deactivating groups decrease reaction rate relative to hydrogen atoms in the benzene ring by electron withdrawal. This can also occur by inductive effects and lone pair activity. The next thing we will look at is to see if a group is ortho, para, or meta-directing based on the intermediate stability, such as what is shown below. We will notice that this is heavily dependent on the substituents of the benzene ring, and is based upon whether or not they are activating or deactivating groups. As you can see, activating groups are ortho and para-directing, whereas deactivating groups are meta-directing. So as we said before, we can determine if a substituent is an activating group based on if it's an electron donator. And this can be seen by inductive effect or lone pair activity. First, we can look at the molecule methylbenzene and see how this methyl group contributes electron density to the ring. This is done by inductive effect. The first important part of observing inductive effect is to look at the atom of the substituent directly connected to the benzene ring. The carbon of the methyl group has an electronegative charge higher than hydrogen, which makes the partial charge negative on this atom. This means it's able to pull the electrons from the hydrogen atoms towards itself, and therefore makes it easier to contribute the electrons to the benzene ring. The methyl group is considered a sigma donor because the single bond is where the electrons can be contributed. The next molecule we will look at is hydroxybenzene to see how these lone pairs of the hydroxyl group can also contribute to the ring and make it an activator. Sigma donors seen in inductive effect contribute electrons to the ring by sigma bonds, whereas pi donors contribute by lone pairs, creating pi bonds. At first you might think that since oxygen is more electronegative than carbon, it will pull electrons away from the carbon bond. But this is outweighed by the fact that the lone pairs of the oxygen atom of the hydroxyl group can actually form a double bond with the adjacent carbon atom. Therefore, the pi bonding is more significant and shows how electron density can be contributed to the benzene ring. The opposite is true of deactivating groups, which are electron withdrawing and do not contribute to the benzene ring by inductive effect or lone pair activity. First, let's consider trifluoromethylbenzene and see how the inductive effect in this case is different from the methyl group we saw before. In this case, the carbon of the trifluoromethyl group is a lot less electronegative than the fluorine atoms, which is why the fluorine atoms will pull the electronegative charge. Will pull the electrons towards it and away from the ring. This gives the partial negative charge on each fluorine atom and partial positive on the carbon, which makes it a sigma acceptor because it wants electrons. Now we could consider a molecule like acetophenone or any molecule that has a carbonyl group. In activators, we looked at the ability of lone pairs to create pi bonds. Now we can see how resonance causes deactivating groups to be pi acceptors and actually remove electron density from the ring. In this resonance form, the adjacent pi system contributes electrons to the carbonyl and kicks off the double bond from the oxygen, leaving an extra lone pair and a negative charge on the atom. This then leaves a positive charge on the carbon where electrons were removed and decreases the rate of electrophilic aromatic substitution. The key to this is to notice that deactivators are substituents which already have double bonds within the molecule. Halogens as substituents are also tricky, but they're also considered deactivators. This is mostly because they react at a slower rate than benzene, so let's look at why. This may confuse you because if we look at fluorobenzene, for example, you can see that a lone pair from the fluorine atom can contribute to the benzene ring, making it a pi donor. But this is outweighed by the fact that fluorine is also a sigma acceptor and is much more electronegative than the carbon atom adjacent that is connected to the benzene ring, which causes the electron density to be pulled towards the fluorine atom. A simple rule to remember is that all halogens are deactivating. So the next part of this learning objective is to see if a group is ortho, para, or meta-directing based on intermediate stability. Just to review, the ortho position is when the electrophile adds exactly one carbon away from the substituent right next to it. Para is when the electrophile adds directly across from the substituent, so 1, 2, 3 carbons away. And meta is when the electrophile adds only 2 carbons away from the substituent. Only 1 carbon is left in between. So activating groups and halogens are both ortho and para directing. Even though halogens are a little confusing, we'll talk about that later. So first we could look at methoxybenzene and see how the oxygen atom of the alkoxy group has lone pairs that can form a double bond and contribute to the electron density of the ring. So if we look at the EAS reaction of methoxybenzene, the electrophile is added to the ortho position. When we look at the methoxy group, because it's a pi donator, it's important to look at the resonance forms of the molecule. Carbocation stability is the most important thing to recognize when determining ortho-para addition. As you can see in this molecule, the ring is stabilized because the carbocation is on the oxygen atom, which leaves each carbon within the benzene ring with a full octet. There is a double bond and 2 bonds, making 4 for this carbon. There's 4 bonds on this carbon, 4 on this one, 4, 4, 4. Now we can look at the same methoxybenzene molecule, but instead of electrophilic addition occurring at the ortho position, it will now occur at the para position. Like I said before, examining the resonance forms of each molecule is really important because, as we can see, similar to the last one, the carbocation is not destabilizing the benzene ring. Instead, it is acting upon the oxygen atom, and each of the carbons within the benzene ring have a full octet. Even though it's very rare, we can see why in the reaction we showed before, the meta product is not favored with this methoxy group or any activator. In the rare case that it does happen, you can see that these resonance forms prove that it's not favored because of the carbocation destabilizing the benzene ring. In none of the resonance forms that this offers will the carbocation be on the actual activating group or substituent, and instead it leaves the carbons on each of the resonance forms without the full octet. So like we said before, halogens are always a special case because they're pi donors and they're also sigma acceptors. They're ortho and para activating just like the activators are. If you look at the resonance forms of the ortho product, you can see that the most significant resonance form has a carbocation on the Cl rather than in the benzene ring. It's on the chlorine atom. Similarly, in the para product, the lone pair of the chlorine atom can also stabilize the carbocation in the benzene ring and leave each carbon atom with a full octet. On the other hand, if the electrophile was added at the meta position, you can see that in the chlorobenzene, you can see that the carbocation will still destabilize the ring no matter what resonance form you try to put it in, and this carbon will be left unsatisfied without the full octet. So with the exception of halogens, deactivating groups are always meta-directing. In this reaction, the trifluoromethylbenzene undergoes electrophilic aromatic substitution on the meta position. As we saw before, haloalkyls are deactivating groups because the carbon's connection to electronegative atoms like fluorine pull the electron density away from the benzene ring. If we look at the resonance form of this product, it isn't clear why the meta position is favored for addition because each carbocation still leaves the carbon atoms without satisfying their octet. But if you observed what happened with the potential ortho and para product resonance forms, such as these shown, you would observe that the carbocation is actually less stable in these two options than in the meta-resonance form. The metacarbocation intermediate is much more stable in the meta-resonance than that of ortho and para addition, because the carbocation in ortho and para addition is adjacent to the substituent. So just for the sake of time, I'll summarize and then give you a few practice problems with answers on the next slide. So activating groups are listed, and they're all ortho and para directors, and deactivating groups, with the exception of halogens, are all meta directors. So here are some practice problems, and the answers will be given on the next slide. Nitration gives two products because this activating group is an ortho and para director. Sulfonation only gives one product because the deactivating group is a meta director. This activating group also gives two products, ortho and para, and the bromination also gives two products because even though it's a deactivating group, it's a halogen, so it favors ortho and para position.